As we have seen, electric charges create an electric field in the space around them. It is useful to have a kind of map that gives us the direction and strength of the field at various places. The English physicist Michael Faraday proposed an idea that provides such a map, the idea of electric field lines. Since the electric field is the electric force per unit charge, field lines are also called lines of force. To introduce the electric field line concept, consider the space around a positive point charge plus Q. At all locations, a positive test charge would experience a repulsive force, and, if we took the time, we could move the test charge around and map out the entire area. After just a few points, we can see that the electric field created by the positive point charge is directed radially outward. The electric field lines are lines drawn to show this direction. They begin on the positive charge and point radially outward. The electric field lines are always directed away from positive charges and toward negative charges. The electric field lines shown here are drawn in only 2 dimensions as a matter of convenience. However, field lines radiate from charges in 3 dimensions, and an infinite number of lines could be drawn. However, for clarity, only a small number are ever included in pictures. Here we've mapped out the field lines in the vicinity of a negative point charge. In this case, they are directed radially inward because the force on a positive test charge is one of attraction, indicating that the electric field points inward. As we've just stated, electric field lines are always directed away from positive charges and toward negative charges. The number of lines that emanate from a given charge is chosen to be proportional to the magnitude of the charge. Thus, 5 times as many lines would emerge from a plus 5 Q charge as from a plus 1 Q charge. The pattern of electric field lines also provides information about the magnitude or strength of the field. Notice that the lines are closer together near the charge, where the electric field is stronger. At distances far from the charge, where the electric field is weaker, the lines are more spread out. In the case of a single point charge, we see that the field lines gradually spread out, meaning that the field gets weaker as the distance from the charge increases. It is true in general that the electric field is stronger in regions where the field lines are closer together. In fact, no matter how many charges are present, the number of lines per unit area passing perpendicularly through a surface is proportional to the magnitude of the electric field. In regions where the electric field lines are equally spaced, there is the same number of lines per unit area everywhere, and the electric field has the same strength at all points. For example, the field lines between the plates of a parallel plate capacitor are parallel and equally spaced, except near the edges where they bulge outward. The equally spaced parallel lines indicate that the electric field has the same magnitude and direction at all points in the central region of the capacitor. Those curved field lines that bulge out of the edges are called fringe fields. Often, electric field lines are curved, as in the case of an electric dipole. An electric dipole consists of 2 separated point charges that have the same magnitude but opposite signs. The electric field of a dipole is proportional to the product of the magnitude of one of the charges and the distance between the charges. This product is called the dipole moment. Many molecules, such as H2O, have dipole moments. We could map out the field everywhere with a positive test charge. Initially, we'd find that the electric field would point away from the positive charge and toward the negative charge, as it should. The entire map is a little complicated and looks like this. For a curved field line, the electric field vector at a point is tangent to the field line at that point. The pattern of lines for the dipole indicates that the electric field is greatest in the region between and immediately surrounding the 2 charges, since the lines are closest together there. Notice that any given field line starts on the positive charge and ends on the negative charge. This is a fundamental characteristic of electric field lines. Electric field lines always begin on a positive charge and end on a negative charge and do not stop or start in mid-space. Furthermore, the number of lines leaving a positive charge or entering a negative charge is proportional to the magnitude of the charge. This also means that the lines must begin and end on equal amounts of total charge. The electric field lines are also curved in the vicinity of 2 identical charges. The patterns associated with two positive point charges shown here reveals that there is an absence of lines in the region between the charges. The absence of lines indicates that the electric field is relatively weak between the charges. We conclude with a list of properties of electric field lines. Field lines are directed away from positive charges and toward negative charges. They begin on positive charges and end on negative charges. They never stop in mid-space. They never cross. The number of lines entering a positive charge or leaving a negative charge is proportional to the magnitude of the charge. Finally, the density of lines at a point is proportional to the magnitude of the electric field at that point.